kind of start out. I was going to draw on the board to kind of put things in perspective. You know, we have this reaction with two reactants, and their stoichiometric coefficients going to form products, and we can come up with the rate law expression, how fast the reaction is going to proceed from left to right is equal to the rate law constant K, and we've talked about how that's pretty exciting. You can find things in there, times the molar concentration of the reactants raised to the reaction order. And we said you can only get those reaction orders by experimentation. We kind of did a couple different ways. Experimental data, one way or the other. So I'm going to talk about kind of reaction mechanisms are kind of the behind the scenes. And actually, these are steps. These are steps that are behind the scenes to get your overall reaction of interest. Okay, these are what we call elementary steps. And this is your reaction of interest. Reaction of interest. I'm just trying to think, if I picture that, that's what I picture. Reaction mechanism would be the roadmap. You know, we just assume that, well, yeah, those two react. Well, there might be a little more complicated behind the scenes.
Is it like that law that we did in chemistry 1?
It is like Hess's law, where, yeah, these all add up to this. Yeah, It is kind of like Hess's law. Yep, exactly. So the mechanism is kind of a step-by-step description of how it happens. And kind of as I have these 1 through 5, you have to do step number 1, and then but this is different than Hess's law. Hess's law is, well, I don't know. It's a little different.
Okay.
Because these do go in order.
Oh, okay.
Yeah, these do go in order. And it's like what's really happening, atom to atom to molecule to molecule. So as I've listed them, these five, okay, these are elementary steps. Okay, these are elementary steps. This is our reaction of interest. And our reaction of interest actually has an overall rate law. Okay? So like this says, elementary steps will add up or sum to the overall reaction. We're gonna add these things. So I pause because now I'm going to talk about some things that I don't want you to confuse. These are actually chemical reactions. I don't want you to confuse these chemical reactions with this chemical reaction. And I bet you might. I hope you won't. Okay? Because we have some exciting things going on with regard to these elementary steps. And one of them is what we call molecularity. Molecularity is the number of participating particles in an elementary step. Okay? And so molecularity comes from the number of particles on the reactant side. I have some examples to show you. It's easier to show you what I mean by molecularity. So molecularity, so these are elementary steps, 1 through 5, and we can talk about molecularity. You cannot talk about molecularity for this guy. You can talk about molecularity for this guy. You're like, why is that so exciting? I will show you why that's so exciting. So for instance, if you only have molecularity, that is the number of, I'll put R for reactant particles. So if you only have one particle, it's what we call unimolecular. 2 particles, bimolecular. 3 particles, termolecular. So literally you're counting the number of reactant particles. And again, it's going to help to show you a picture of what your kind of options are. So for instance, reactant A go to form product B. This is a unimolecular elementary step. This would be a unimolecular elementary step. This would be an example of a bimolecular elementary step. Too many words here. Bimolecular elementary step. Notice that this would be what? The fourth one up there, this is 2A going to form B. Bimolecular. Okay. Now, ter or trimolecular. I go back and forth between TER and TRI, so you'll just have to kind of catch me where I go. A trimolecular elementary step would look like this, where we have 1 particle of A, 2 particles of B. But I'm going to try to convince you that this as an elementary behind the scenes step is not very likely. Because, well, if you've ever tried to get your friends together, it's easier to get one friend together than two friends together. I don't know if that's a good example, or three friends together. They literally have to occupy the same space or similar space to proceed from reactants to products. So termolecular is kind of hard, kind of not very likely actually. So instead of termolecular, what appears to be termolecular actually probably happens in two steps. So down here, I'm going to kind of show you, for instance, I'll put a question mark up here. Somebody's like, hey, this is an elementary step. Are you like, really? I think it probably occurs like this. I'll give you kind of your first, we've added equations before. If I add these equations, let's see, my D's are going to cancel because they're on both sides. Does that make sense? Or I can just do it this way. Add them together, I get 2B plus A plus D goes to form D plus C. And we know we can clean things up. D's will go away. My point on this slide is just to try to show you that what somebody is a solid elementary step. You're like, are you sure? It might really be two different elementary steps. That's all I'm showing you here. Because this is more likely. This actually introduces another thing I have on a slide coming up. Do you see where D was created in the first elementary step and consumed in the second elementary step in its entirety? Mm-hmm. It's like a ghost. And D actually we're going to call an intermediate coming up. It's like, it's there, it's created, but it's kind of just on the way through. Okay, so. All right. Maybe. Got mad at me. Okay. So here's the deal. The rate equation for, I'm going to read this. I don't read many slides. But the rate equation for a chemical reaction cannot be predicted from stoichiometry. In other words, the rate, what says rate equation, I could change it to, you cannot get the reaction orders, M and N, from these stoichiometric coefficients. You cannot. You cannot. It's a reaction of interest. I want to scream that because if your step is an elementary step, we're actually going to play around with, for each elementary step, we are going to write rate law expressions. Okay? Reaction rate laws, or whatever you say. Rate law expressions. And we are going to use molecularity as their reaction orders. Don't ask me why it works this way, but that's how it works. Okay, if you are dealing with a reaction that's an elementary step, you know the reaction orders. Now you can imagine why I'm pausing at this point in this material, because what I don't want you to do, and what you can't afford to do, is to get this confused. And on a test, when I say, what's the reaction? Here's the overall reaction of interest. What are those reaction orders? You're going to say, I can only get them by if you give me experimental data. And I'm going to give you experimental data. What you can't do is use their stoichiometric coefficients. In elementary step, you can. Okay. I think I've belabored that hopefully enough.
So you can't do it for the reaction of interest, but you can do it for the elementary steps.
Yes. Not only can you, but we're counting on you to be able to. We're going to turn their coefficients into their reaction orders.
Okay.
Yep.
For the
elementary steps.
elementary steps, but not every reaction.
Not ever. Sometimes it's coincidental, but yeah, you cannot use A and B and turn them into reaction orders. But that's what we're counting on for the elementary steps. Sounds like you guys got it. Yay! So let's kind of see what that looks like. So for an elementary step, when we come up with their individual rate law expressions, we're just going to use their stoichiometry, like the coefficient of 1 or 2, to say it's first order or second order. And we're going to come up with these these rate law expressions for these guys. Cool. For instance, and actually, so this is like the homework that you're going to do for Monday. You're going to kind of pull yourself through. You're going to have a whole list of, well, this is an elementary step. What is the rate law expression for that elementary step? And it looks like this. We know that we're going to take rate, K is equal to K times the molar concentrations of the reactants raised to the reaction orders. And if it's an elementary step, their reaction orders is going to be your stoichiometric coefficient. So coefficient for A is 1. So that's first order. That's it. There we go. Here's another one. Get excited. We have 2 reactants. So we know the rate law expression is going to have to be the molar concentration of A and B. Well, K times the molar concentration of A and B raised to the reaction order. Since our coefficients are 1, it's first order. Okay? Because it's an elementary step. Here's one for you. Second order. Okay? Isn't that nice? Okay. All right then. Okay. Now here's one for you. This is funny because like getting out the door. If you picture you're at home and you have, I don't know, 4, 5, 6 family members. Maybe you have your cousins spending the night, and you're trying to get to church in the morning. There's that one person that's going to take a little more time than everybody else. And if you're going in the same car, that is actually going to determine when you get to where you're trying to go. So here's the deal. Of these 5 steps, one is going to be slow. And that's actually kind of when we work problems. One is going to be slow, and that's going to be what we call the rate determining step. Okay? So, you know, if I have 5 here, and I'll put F for fast, okay, fast, 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 I'll put in slow, fast, okay. So this one right here, that one is what's going to slow us down. Go fast, 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 slow, fast, and we're done, okay. That's kind of like the person that's slow in your house. So here, when we go to, if we have a mechanism like this, I've never done this on the board like this, I'm kind of like this. So if we know a mechanism behind the scenes, we have identified the slow one, does this make sense that it's this slow one that actually is going to drive our overall, it's going to be most like, and actually, how do I say this? I think this is how it's going to work. If we know what this is, then we know what this is, because it's driving our observed reaction rate. Okay? That's it.
So,
these other ones are behind the scenes, and it's not quite this simple, but if I know this rate law expression, actually that rate law expression is going to be our observed, the observed overall rate for the reaction of interest. Yep. Yep. Okay, so the slow one is rate determining. Sometimes it's called a rate limiting step, but I usually call it rate determining. Rate determining. Ooh. And you might be wondering, well, how am I supposed to know? Well, they tell you. They will tell you that one's the slow step, rate determining step. All right. So, got some possibilities. For instance, if the slow one is early on, say it's the first one, then it goes slow, 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 fast. Okay? For instance, we've changed it up. If the slow one is down here, then we go fast, slow. So they are going in order. I mean, it's like a skit. It's like a narration of how it's proceeding overall from reactants to products. This is what's happening behind the scenes.
So if the slowest reaction is the first one, its rate is still equal to the
yes.
reaction.
Yep. If this was slow, this rate would be equal to the observed. Because these guys are just, they're flying by. They're not slowing us down at all. And this, yeah.
How do we know that?
How do you know it's slow?
Yeah, and how are we timing the different elementary steps?
That's going to have to be given to you.
Oh.
Yeah, and it won't, and in this sort of problem, we're not going to actually be given rate information, but we'll be given relative. One will be slow, and if you're like me, I'm like, well, what two are slow? But in these sort of problems, one is slow and the other are fast. And there's no really rate information given, it's just relatively speaking. Good questions. So D, a little bit ago, the ghost thing, that was a reaction intermediate. Okay, so something that's formed in one elementary step, but then gobbled up in another elementary step. So you'll see it formed as a product, and then it will be a reactant, and we all use that. Okay, but this is kind of fun. It's sometimes possible, the whole D thing. It's sometimes possible to snag it, and that'd be fun. It's like it's a ghost, but it's isolatable. It's exciting, and sometimes not so much. It's not stable, so you can't really snag it. Now, let's see. Now, when this is talking about the proposed mechanism, this is the, proposed. So all of these 5 steps need to be consistent with what we observe. Okay, what we observe with regard to our reactants, changing the molar concentration of reactants, what we observe with our products, the rate law expression itself, and if we're going to tweak it by adding inhibitor or catalyst. Remember, we talked the other day when we talked about activation energies, actually not inhibitors, but I know catalysts are related to activation energies in that they lower activation energies and provide, this kind of hurts my brain, the way catalysts work, they lower the activation energy by providing an alternate mechanism for your reaction to occur. Catalysts are not consumed, they're optional, but they speed it up by making a different mechanism. Okay, so mechanisms. Now, if you have, now this is like an oxymoron thing, it feels like, but if you have a mechanism that just has a single elementary step, okay, then you have a special situation. Yeah, the word is, where did I?
Concerted reaction.
Yeah, concerted reaction. But it's an elementary reaction too. Okay, yeah. So make sure we're all on the same page. Yeah, concerted reaction. But here in my slides, it can also be called, just an elementary reaction. Like, wait, elementary step, elementary reaction? What are we talking about here? Somebody says, I have a reaction of interest, and it's an elementary reaction. That means it only has one elementary step. Okay, one elementary step, so it's an elementary reaction. Well, dang, if that's the case, what we know is we can use molecularity with elementary steps, and if that is equal to that, then we can use molecularity, and that's totally it. We can use the stoichiometry, if we know it happens one step, to get our reaction orders, and you're right about that. So for instance, this happens to be one such elementary reaction. They have to tell you that.
Mm-hmm. So every reaction that, like, everything that we went through so far, like every reaction has elementary steps, right? Like,
yes,
okay.
Every reaction has elementary steps. That's the way I think of it. But in some cases, and those elementary steps are what we call the mechanism.
Okay.
That's a powerful step.
Mm-hmm. And when it's just one elementary step, the elementary step is equal to the reaction.
Right. Yep. Does that make sense too? Yeah. When it's just one elementary step, then that is equal to that. Yep. And so this just happened. We're going to look at a couple that are elementary reactions. So they have one elementary step in the mechanism. And so we can use molecularity. Yeah, that was just trying to find the word elementary reaction. I think I've got too many slides here with pictures of this. I don't know why. N2O plus NO goes to form N2 and NO2. So are you ready for the slideshow? Okay. But just as we were talking, yeah. So since this, the kind of adding up the elementary steps has to be equal to this, sorry, this. Okay, so this has to be equal to this overall reaction of interest, and there's only one. It's like what we were just talking about, that one must be that. Yeah, anyway, you guys got it. So here's my pictures. I don't know, too many. This is N2O, NO, showing these are the Lewis structures, lone pair electrons. Okay, it goes to form, but this does have a D. This does have, no, this isn't a D. It's actually, sorry, I mean to throw you off. We're going to see an energy diagram here in a minute where this is actually the top of our activation energy. I don't know if you guys remember that. The top of our activation, or top of our energy pump. Mm-hmm. That actually, top of our energy barrier, that is kind of that's not isolatable. That is a transition state. And then they go ahead and separate. So this guy goes over there, so it ends up over here, and we end up with N2. So those are the products. Again, far too many pictures. Here we go, another one. Okay, there's our N2O. There's our O2. There's our products. Too many. Oh, that was NO, sorry. Another one. Okay. Again, you're going to see it here in a minute. This is not an intermediate. I'm sorry. There's a difference between intermediate, which actually is something that's formed as a product of an elementary step and then consumed as a reactant in its entirety of another elementary step. This is actually at the top of our energy, you're going to see here in a minute, barrier. So here we go. This is what I was trying to show you. This is kind of the between reactants and products. Okay, there's our transition state. So we actually looked at this exact energy diagram the other day. And remember, the way this works is we look at, if we're going from left to right from reactants to products, this difference right here is your change in your enthalpy of the reaction. And in order to get the activation energy, we go, since we're going from left to right, we go from this energy up to the top of our energy barrier. So that is our activation energy. Okay. Now, I don't mean to necessarily confuse you, but if we turn this into a two-way arrow, go that way, then these become our reactants, and this becomes our product. Of course, the change in enthalpy will be the same magnitude, but it will be positive. And now in order to get the activation energy, we go from where we started energy-wise to the top of the energy barrier. So there is our activation energy in the reverse direction. One more in the forward direction. A little slower. Yep. Kind of a busy slide. Okay, so again, going back to what we said a few slides ago, it said that this particular overall reaction is an elementary reaction. So you guys told me then that is an elementary step. Okay. So we can use molecularity. Coefficient of 1, those are both first order. So we can go ahead, bada boom, and go for the rate law expression using molecularity. Okay. This is another one that is an elementary reaction, very special thing. So since it's an elementary reaction, we can use molecularity, which actually, I'm going to show you the balanced equation. We have 2HI going to form I2 and H2 and I2. And this is a thought how it might work. This would be our transition state. Isn't that funny looking? Okay, so this would be these two molecules together, and then they break apart into the products. So the products are the H2 and the I2. So just this morning, before I got ready for my classes, I went ahead and inserted this. This is a balanced equation for the reaction of interest we just saw. again, since it is an elementary reaction, we can use the molecularity of the reactants to turn those into reaction orders. Okay. So the reaction order would be HI would be second order. Okay. Well, that's probably, it gets a little more complicated from there. Sounds like you guys got kind of the gist of that. What if you have a mechanism that doesn't have 5, but we'll kind of tame it down a little bit, but has more than one elementary step? Well, in that case, you're going to have to look for the rate determining step. And I've already kind of shown you that that's actually going to have to somehow be plugged right back into what we observed. That one's going to be used most. So let's do one where, let's see, the mechanism consists of an initial slow step, so it's going to be rate determining, and a second fast step. And this isn't a good example of it. So this is our reaction of interest. It's not an elementary step, it's reaction of interest. And they did some experimentation, and they came up with overall first order for H2, overall first order for ICL. First order. And I think my next slide says something like this. You know it was not an elementary reaction because we could not use molecularity from the reaction of interest to turn them into reaction orders. Okay? Because that would have been a 1, that would have been a 2. Okay? It's not an elementary step. Must be something else happening behind the scenes. And this is kind of, what I'm showing you on this slide is kind of the way problems go. They suggest a possible mechanism, a possible set of elementary steps. So here we go. What if, let's just throw this out there, your one molecule of H2 combines with ICL to make HI and HCl, okay? And then your HI combines with another molecule of ICL to make I2 and HCl. Now if I draw a line and I add them together, I come up with this. Okay, so I had 2 ICLs, 1 H2, and the HIs, you can see I've gone ahead and canceled them. Those are that is an intermediate. Okay? So the way this works is you come up with, usually it's not just a single elementary step, usually it's 2 or 3 or 4 elementary steps behind the scenes that gives you overall reaction of interest. The other thing is you have to focus on your slow one, this guy right here, and you'd be like, oh, well, if it is slow, then I can use, sorry, it is not slow. Well, if it is slow, my overall observed rate is going to be based upon that one. And it is an elementary step, I can use molecularity to knock out the rate law expression. So, hey, that works. Okay? If we focus just on that first step, which is rate determining, the first step is slow, and I put a 1 here. And that 1 is to remind me that that's actually a rate from an elementary step. This one is the rate.
So, if we pick the lowest one, we know its rate is going to be the rate of the reaction of interest. Mm-hmm. But the reaction order of that reaction, they're not going to be the reaction order of the reaction of interest, right?
No, it will be.
Oh,
we can use molecularity. Yeah, it's exciting. Okay. Because like this one, I think this is what you're saying. So we can use just kind of like the examples we did before. I can knock out a rate 1. This is how I do it in my homework. You call it rate 1 because that reminds me it's an elementary step, is equal to K-RON, the rate law constant associated with that elementary step, and then the molar concentration of H2 raised to the first power, and the molar concentration of ICL raised to the first power. That's using molecularity.
Okay.
Mm-hmm.
And so that's the rate of the overall of the reaction of interest.
Yep.
Okay.
Now on somewhat apologetic because it might be on your test. On Monday, I'm going to kind of take it up a notch, and the only difference what I need to introduce Monday is sometimes you end up with a slow step, basically that has an intermediate, and you can't have an intermediate in your rate law expression. So on Monday, I'm gonna have to fix you how to fix you. On Monday, I'm gonna have to kind of tell you how we tease out that in terms of real reactants. So, but yeah, yep, that's it. So that's why down here, that's why on this next slide, you see, based upon all that, the slow, and since it's elementary, I can use it for molecularity, since coefficients in front of those two reactants were 1, you're looking at first order for those two things. And again, so again, back to Monday, and the fact that there's no intermediate here, I'm done. I'm totally done. Done with this. Okay? So the difference, it's a subtle difference, but in order to go to the real rate law expression, notice that kind of as a side, I said for the overall reaction of interest, the rate will be equal to K, molar concentration of each of the reactants raised to their first power. But I kind of know behind the scenes that rate law constant, K, actually is really K1. So.
But then back a slide, it was K2 for the second elementary step.
This one?
Yeah.
Yeah. Yeah, if we were coming up with, yep, if I was to write for that second elementary.
You wouldn't really write it for the second because it's
Right, because it's fast. Yep, we kind of blow it off. And the other thing, and again, this is a good example of why we need Monday, is I could not, if this was slow, I would go to do this, right? If it was slow, like what you're saying, I go rate 2 is equal to the molar concentration of HI times the molar concentration of ICL, both raised to the first power because that's your supplementary coefficient. I could not stop here because I have an intermediate. So I'm going to show you how to fix that. Okay. Yep. I don't think you guys got it. I just need to explain to Daniel. No. Daniel, are you listening? Okay. Okay. So let's see. Oh yeah, this is kind of neat. So if you have 2 elementary steps, you could have 2 little humps here. Okay. Each kind of. Well, I think I can break this up. Okay, this would be your reactant. This would be the product of your first elementary step, and this would be your overall products. Okay, so it goes you. Notice that little hump in both, we have an activation energy associated with each elementary step. Okay. So this would be the change in enthalpy for the first elementary step. This would be the change in enthalpy for the second elementary step. And this would be the overall change in enthalpy. Combine that. And that hump is that activation energy for the first step. And this little hump is the activation energy for the second step. And this could actually be, maybe it was supposed to be, this diagram associated with the last mechanism we talked about. Because we said the first elementary step was rate determining. Okay, so a higher activation energy, a slower rate. Okay, and this one was faster, second elementary step. Again, it's kind of a similar diagram where you see the 2 elementary steps must be going on behind the scenes. Kind of marking a few things we've talked about. At the top of an energy barrier, at the top of the energy barrier would be our 2 transition states. Okay. So this is our overall enthalpy for the chemical reaction. Excellent. Stop here. Let me think. Okay, so these, and I'll let you jot them down. So there's 5 problems here. These are ones that you can definitely do. It's kind of nice. I don't know if we could have gotten through all the slides. Maybe could have, but this will give your palate a chance to kind of clear and come back and finish up Monday with these slides and then talk about reaction orders that aren't whole numbers. That's kind of fun. just a quick slide. And then on Wednesday, I mentioned we're going to go ahead and do a review slides. I've gotten good feedback for this particular unit, just doing PowerPoints that talk you through. That's getting out early in all my classes. That's how we're in stuff.